Welcome to AI Peer Review. Today, we're sort of moving past the standard ways we think about AI reasoning.
Yeah, for a long time it's been chain of thought, right? LLMs basically thinking with text.
Exactly. And more recently, we've seen models start to think with images, generating visual steps too.
But, both of those they have real limitations. Text can be hard to follow sometimes.
And images are just snapshots, aren't they? Static moments.
Right. They can't really capture dynamic processes, things changing over time, like physics.
And there's often this disconnect, this struggle to truly unify text and vision into one coherent thought stream. So that brings us to this interesting paper and a newer idea, thinking with video,
Ah, yes. Using these huge video generation models like Sora 2.
to try and blend text and visual reasoning inside a temporal framework over time.
Exactly. The thinking is, if the AI can actually simulate drawing something or imagine a process unfolding,
Showing that change dynamically.
it gets closer to a more holistic, maybe human-like way of reasoning. It's not just getting the answer, it's showing how you get there.
Showing the transformation, A to B to C.
Precisely.
And the OpenMOSS work we're digging into today, their mission was really to test this out systematically.
They built this thing called the Video Thinking Benchmark, or Video Think Bench.
Right, designed specifically to probe this dynamic reasoning ability.
And our job today, in this deep dive, is to figure out if this video approach really delivers that unified reasoning we're looking for.
We're putting Sora 2 head-to-head with the big vision language models GPT-5, Claude Sonnet 4.5, Gemini 2.5 Pro.
Okay, so Video Think Bench, it's basically split into two main types of tasks. You can sort of see this conceptually in their figure 1.
What are they?
First up are the vision-centric tasks. These are problems where you pretty much have to draw or simulate visually.
Like using imagination to solve it.
Yeah, testing spatial skills, inductive reasoning, things like geometric puzzles, they call them eyeballing puzzles,
Yeah.
and abstract stuff like ARC, AGI2.
Okay, vision stuff. What's the second category?
That's the text-centric tasks. Here, they took existing benchmarks, like math or MMMU subsets,
Standard stuff.
and made the video model reason through them visually. It has to, write out the solution steps in the video.
And draw graphs, maybe.
Right, and then present the final answer.
Yeah.
All happening dynamically into the video.
Okay, let's dig into those vision-centric ones first. The eyeballing puzzles. You said geometry?
Yeah, pretty tricky geometric reasoning, like find the missing vertex of a parallelogram or figure out where a ray of light reflects.
Or find the center of a circle just by looking, stuff like that.
Exactly. But then the question is, how do you actually score a video answer for correctness? It's not just a single image.
Yeah, that seems tricky. What do they do?
Well, this is where it gets technically interesting. Sora 2 outputs the video and a spoken audio track, right? So they didn't just evaluate the final frame. They used 3 methods, but the really key one was the major frame evaluation.
Major frame evaluation. What's that involve?
It means they sample frames throughout the entire video, not just the last one. They aggregate the information across time.
Ah, so looking for consistency over the duration of the video.
Precisely. And they found this major frame method gave the highest overall correctness, 40.2%.
That's quite a bit higher than just looking at the last frame, which was 33.4%.
Yeah, and much better than just listening to the audio track, which only got 28.0% on these vision tasks.
So it's like the AI's confidence isn't just in the final picture, but in holding that belief, that visual representation steadily over time.
That's a great way to put it. That temporal consistency seems to be a real advantage of thinking with video.
And how did Sora 2 stack up against the others using this major frame score?
Pretty well, actually. That 40.2% overall score generally beat the big VLMs. Claude 4.5, for instance, got around 35.1%.
Okay.
But here's a really standout result. Look at Table 2 in the paper. On specific geometric tasks like ray intersection, Sora 2 nailed it. An incredible 88% accuracy.
Wow, 88%. That's not just drawing, is it? That's like simulating the physics, the geometry accurately over time.
It really suggests the video model has a stronger inherent grasp of dynamic rules and cause and effect compared to models only seeing static images.
It's actually imagining the process.
Yeah, it seems like that spatial strength is pretty clear.
What about the other vision tasks, the inductive ones, like visual puzzles?
Right. Pattern finding, color filling, drawing shapes, mentioned in Table 3.
How did it do there?
Sora 2 performed pretty competitively. Its overall score was 66.2%. Maybe a bit behind the absolute top VLM, like Claude Sonnet 4.5 at 78.8%.
Okay.
But very close on specific things like shape drawing puzzles, Sora 2 got 64.9% there versus Claude 68.6%, so definitely holding its own.
So the first takeaway seems clear. For tasks needing dynamic simulation, visual imagination, thinking with video shows real promise, real strengths.
Definitely. But now we get to the part that sort of complicates the picture. The text-centric tasks.
Right, the math and general knowledge stuff, where the model has to show its work visually.
Yeah, remember the setup text prompt in, maybe a reference image, and Sora 2 generates a video. In the video, it's writing out the solution.
Like on a chalkboard or paper.
And then it speaks the final answer in the audio track. You can see an example in Figure 5.
Okay, and the results here were unexpected.
Highly unexpected, particularly the audio accuracy. Check Table 5. Sora 2 was getting scores comparable to, sometimes even beating, top LLMs on their own turf.
Like on what benchmarks?
Get this. GSM 8K, that's pretty complex high school math problems.
Yeah.
98.9% audio accuracy for Sora 2.
99%. Seriously.
Seriously. Math 500, 92.0%. Multimodal general knowledge, Bench, 89.0%. These scores are phenomenal for what we think of as a video model.
How is that even possible? A video generator being a near-perfect math solver?
Well, that's the million-dollar question, isn't it?
Yeah.
And it leads directly to what the paper calls the modality gap.
The modality gap. Explain that.
Okay, so across all these text-based tasks, Sora 2's audio accuracy was high, averaging 73.6%.
Right, speaking the correct answer.
But its last frame accuracy, judging the correctness based on the final visual frame of the written solution, was way lower, only 56.3% overall.
Ah, so it says the right answer, but the written work it shows is often wrong or unclear.
Exactly. It's like that brilliant student who aces the test verbally, but their written notes are completely illegible. The logic's just gone.
It's a bit strange, like the visual reasoning isn't keeping up with whatever part is getting the answer.
Precisely. They actually did a manual analysis, shown in Figure 6, looking at cases where the audio answer was right.
And what do they find in the videos?
It confirmed the problem. A huge chunk, 43.48% of the video solutions, were labeled unreadable or incorrect logic.
Over 40%.
Yeah. And only about 14%, 13.91% to be exact, showed completely correct written reasoning steps.
So wait a minute. If the video is often showing garbled logic for math problems, what's the point of using video for that? Isn't traditional text-based chain of thought just better for logical steps?
It definitely raises that question. And more fundamentally, it makes you ask, where is the real reasoning happening?
If the video part isn't doing the heavy lifting for the logic,
then the high accuracy must be coming from somewhere else. Maybe something happening before the video generation even starts.
Okay, so that prompted an investigation into the source of this ability.
Yes, which brings us nicely into the next part. Trying to dissect where this reasoning power truly lies.
How did they start probing that?
First, some confirmation experiments. They checked its few-shot learning ability using that abstract ARCE AGI2 task.
The one needing pattern abstraction from examples.
Right. And Table 7 shows Sora 2 did much better on pixel accuracy when it saw all the examples compared to just one.
So it can do in-context learning. That capability is there.
Yes, that seems inherent, which then led them to look at test time scaling. This is really interesting for video models.
We already saw the benefit of looking across time within one video with major frame evaluation. Can they scale that further?
They can, using self-consistency. Let's go back to a visual puzzle, the Arc Connect puzzle. Remember, major frame analysis boosted accuracy over just the last frame? Table 6 shows this.
Yeah, it went from 56% to 68%.
Okay, now here's the really cool part. They didn't just analyze one video attempt. They generated 5 separate videos for the same puzzle.
5 different tries.
Yes. And then they aggregated the major frame result from each of those 5 attempts and took a majority vote on the final answer.
Self-consistency, but applied to video generation outputs. And what happened?
The accuracy jumped from 68% with one video's major frame analysis to 90% with the 5-video vote.
90%? Wow, that's a massive leap. A 22-point gain just from letting it try multiple times and voting.
Yeah. It shows that combining temporal consistency within a video and self-consistency across multiple video generations gives you a much more reliable signal of the model's actual problem-solving ability.
That seems huge for making these kinds of reasoning tasks more verifiable, more robust.
It's a really promising direction, a potential game changer for reliable dynamic reasoning.
Okay, that's impressive scaling. But let's swing back to the main puzzle. The super high text scores versus the often messy video reasoning. We need that final piece.
The prompt rewriter hypothesis.
Right. How did they test this? First, data leakage?
They tried to rule that out. They tested Sora 2 on math problems that were derived from the benchmarks but had different numbers.
Same structure, different
What
values.
values?
Exactly. And performance stayed strong, as shown in Table 8. So it wasn't just memorizing answers. The ability seemed genuine, but maybe outsourced.
Outsourced how?
This is where the comparison with another model, Wando 2.5, comes in. It's also a video model, but crucially, it has a controllable parameter,
What parameter?
an internal prompt rewriter, basically a component that can pre-process the input prompt.
And they could turn this rewriter on or off?
Yes, and this test was pretty definitive. When they turned the prompt rewriter off in 1.2.5,
What happened to the math scores?
they collapsed. GSM-8K audio accuracy went to effectively 0. It just couldn't do the math problems anymore.
Wow.
But then, when they turned the prompt rewriter back on,
Accuracy jumped back up?
substantially. For GSM-8K, audio accuracy went from 0.0% all the way to 31.9%. Not as high as Sora 2, but a massive difference caused purely by enabling that internal rewriter.
So the implication is pretty clear, isn't it?
It strongly suggests that Sora 2's impressive text-centric performance, the high math scores, it's likely being handled by an internal component before the video generation.
Like an internal VLM or a sophisticated prompt rewriter.
Exactly. That component probably solves the problem using more traditional methods, maybe like chain of thought,
Gets the answer is X.
and then translates that solution into a set of instructions for the video generator. Draw this equation, write this number, say this answer.
So the video part isn't really doing the core reasoning for those tasks. It's more like illustrating a conclusion reached elsewhere.
That seems to be the most plausible explanation based on their findings. It looks like a unified process, but it's likely a two-stage system under the hood.
Okay. So wrapping this up, what's the big picture here for foundation models and AI reasoning?
Well, the core takeaway is that thinking with video is a powerful idea. It definitely offers clear advantages for certain kinds of reasoning.
Especially spatial, physical, dynamic simulation tasks, where that temporal analysis really shines.
Right. But the current state-of-the-art models might be a bit deceptive. We need to be careful about assuming the video generator itself is doing all the reasoning we see.
The challenge is disentangling that native video reasoning ability from these powerful but maybe separate internal pre-processing steps like prompt rewriting.
Exactly. We need to figure out how much is genuine dynamic simulation versus just illustrating an answer from an LLM bolted on internally.
Which leads to the future direction they propose in the paper.
Yeah, they suggest focusing on reinforcement learning with verifiable rewards, or RLVR.
RLVR, how would that work?
The idea is to really lean into the tasks where video is essential and verifiable. Those geometric puzzles, the ARC-AGI challenges from Video ThinkBench.
Tasks where the process shown in the video matters and you can actually check if it's correct.
Precisely. By scaling up training on those kinds of verifiable tasks, you could directly reward and improve the video model's native dynamic reasoning and simulation skills.
Training the video part to actually reason, not just illustrate.
And this leaves us with a kind of provocative thought for you, the listener.
Go on.
If the most effective way for an advanced AI to solve complex problems involves simulating different scenarios, different physical possibilities in a video-like way, and then maybe even voting on the outcomes like we saw with self-consistency.
Yeah.
Does the ultimate architecture for future foundation models look less like a pure text-based LLM and more like a fundamentally unified dynamic video generation system, one that thinks by simulating?
If deep reasoning requires simulating reality and comparing outcomes, that really changes our whole concept of what an intelligent machine architecture might look like.
It certainly pushes the boundaries. Something to chew on.
Absolutely. Thanks for walking us through this really fascinating research today.
My pleasure. Always interesting to see where the edge is moving.